Hey, welcome back, Calcsters. For today, if you are traveling on the road, I'll think this out as we're going. But as a class, we are going to start 5.2. And 5.2 is a pretty big one that we're going to deal with for the next several days. In 5.2, we only have one main idea, and that is the definite integral. Okay, now I'm going to be honest. This can be intimidating when you first see it, but here's the cool part. You've already been doing it. Like, you've already done this, whether you're aware of it or not. So you guys are going to give me some like nice, helpful things here in just a second. And you may use your notes to do this. But if I want to do some recall stuff, if I ask you to find the area between a curve and the x-axis, or more casually said, the area under a curve, we have a way to do this. Area is equal to, and you used this definition like over and over and over on your homework. Anybody remember it off the top of your head? If I want to actually calculate the area. How many rectangles works best? And how do I let the number of rectangles go to infinity? Oh, we'll take the limit. Okay, so it's the limit as n approaches infinity. So nothing new here. Of what? Ooh, I love that. So first one, Abigail says S sub n. Now, there's a natural follow-up question that I have for Abigail and everybody else. What's S sub n? Like, this is the limit as n approaches infinity. And Abigail, I don't know whether you said this because you didn't want to read the monstrosity of the other part. If that's true, that's awesome. Like, good call. But I do want that monstrosity of the other part also. The sum from I equals 1 to where? N of what? F of C sub I. And what does this represent? So whether it's lower or not doesn't matter because we're using infinitely many. But just very specifically for each rectangle, what does F of C represent? The height. Good. And then what else do we need for each rectangle? The width, delta x. Okay. Now we have this, and we used the heck out of it. As we're going through these things, what we wind up seeing, and I like that Rafa said this is a lower one. If we let n go to infinity, does it really matter whether we use the lower or upper sum? Like, we get the same answer either way. So what we could write, and I'm just not writing this, is that if we do the lower and we get an answer, and we do the upper and we get an answer, the other answer is going to be right in between. Like, it's almost a squeeze theorem happening again. The more rectangles I use, the more closely squeezed together that the actual area gets, and we could work it out. Now, as we go through here, all that we're going to start with today is that it turns out that if I have the right endpoint, the biggest value of x, and the left endpoint, any value in between will work. Now, it doesn't matter for sure that it's a left or the right. I could pick the 3/4 point, and it will still work fine as long as there's infinitely many rectangles. Doesn't matter at all where we actually put that endpoint. The right is the most convenient. If we're using these, as a quick reminder, how do we get delta x? B minus a over n. And if we commit to right endpoints, how do we get those right endpoints? So I'll give you guys like 30 seconds or so. I'd look through your notes. I'm going to call in somebody random, so it will be a cold call. But how do we get C sub I? How do we get C sub I is what I'm looking for. Anybody have a good answer? Ooh, you're close. That works. This works really well if we start where x equals 0. Ooh, let's start at wherever a is and just add a delta x I to it. Like, you were super close with that, Ralph. Okay, now we have all of this stuff knocked out here. And we've done some Riemann sums, but we just haven't used this word. Okay, when you eventually decide that you're going to study mathematics and that's going to be your life's goal and purpose, you will encounter the name Georg Cantor Riemann. Like, it's going to happen. Riemann was and is one of arguably the most important mathematicians in the modern world, because he did a lot of work. If you guys have ever seen the oh my gosh, the Mandelbrot set, like crazy fractal stuff, or if you've ever wondered about how to find prime numbers, there's this big idea called the Riemann hypothesis that works out how do you get prime numbers. And if anybody ever solves that problem, say goodbye to all of your computer security. Like, if we have a way to calculate primes, nothing online is ever safe anymore until quantum computing comes by and takes over. So fingers crossed that nobody solves it, or fingers crossed that somebody solves it, because it'd be a huge leap forward in mathematics. Terrible for society, maybe. Either way, we're going to define for ourselves to start this lovely idea of Riemann sums. It does kind of sound like that. You might hear other people say Riemann or Riemann. I pronounce it Riemann. Do you have a way to pronounce this name, Miss Sweet, just out of curiosity? Okay, like I didn't know if everybody learns it a different way. But all right, we have Riemann sums. Now, all that we have to do to make this work nicely, and it'll look ugly, but I assure you it's so much nicer than you think it's going to be. We're just going to simply let some point, u sub I, live in this interval, and any subinterval for that matter. And we're going to say that u sub I is greater than or equal to lowercase c sub I, which, what does this one indicate? The lowercase part of it? The lower sum. And what do you think that this u that's somewhere in between the lower limit, the left endpoint, and the what other endpoint might I choose? And how would I write the upper endpoint? Capital C. Okay, as long as I pick something between them, and that's all that I'm saying with u here, some value in between them. As long as we do that, we find area using, and I'm not going to write the limit out here yet, but we're just going to write this summation. It's the sum from I equals 1 to n, and we're going to write this over and over and over, and we're just going to make one little tiny change. We'll call it f of u sub I, and we're just saying, don't care if it's a left point, the right point, somewhere in between, doesn't matter. It's in the same little subinterval, times delta x sub I. And we're going to pause here for like 15 seconds, because this is the first time that we're saying delta x sub I. Every single time we've done the rectangles so far, the widths, we've made it so they're exactly the same. Now, that's really convenient when it works nicely, but there will be situations, and we'll encounter these. I'm not going to get a real true example ready to rock right now, but in pink, I will sketch it out. You do not have to sketch this. If I didn't want to use equal sized rectangles, like maybe we have something weird that happens, and again, you don't have to sketch this. Could I use, like here, maybe little tiny rectangles make sense because it's such a huge vertical change. Do you guys agree? Over here, would it be okay if this was my rectangle? And I'll still get a good area, right? So all that we're allowing for here, not that we're doing this yet, but when we do delta x sub I, it's possible that we could have different widths of our rectangles. Like, in practice, maybe we won't do it crazy often, but I think, and I hope that I've convinced you that with that pink example, that yeah, there's a time where this makes sense. We all agree with that? Okay. So 2 of you gave me an affirmative. Does anybody not quite understand what I'm saying there? Better way to ask that question. Sometimes bigger rectangles might be useful. Okay, deal. Okay, so as we're looking at this, with this given, we can find the area using this with some assumptions. And I'll go back to blue, because there's a few things that we have to assume. If we were in an analysis course, we would be proving these assumptions. We're not, unfortunately, in a real analysis course. Okay, we are going to get 3 lovely, just kidding, 5 lovely assumptions out of this. Okay, the first one, and these are in no particular order. We're just going to require that whatever function that we're working with, it is defined on a to b, that closed interval. So no gaps, no discontinuities. We need to have our function completely defined. Okay, now every single graph that we have done this far and looked at for the area, it's always been above the x-axis, right? Does every graph that you think we'll ever deal with really truly live above the x-axis? So we haven't done it yet, and we'll deal with it when it happens. But we're just going to say, hey, it's okay. F may be negative. And that's okay. We'll make sense of what this means. It's a weird interpretation, but we'll get practice with this. Okay. Now, beyond that, I'm immediately going to go back, but I'm glad we didn't write it. F is defined. Here's the other statement. I was just wrong, but we haven't written it, so I think we'll be okay. F is probably continuous. Now, if we have a discontinuity, and of course we will, and I don't know what I was thinking when I said this a second ago, when we get a discontinuity, we'll get through it. We'll see that, hey, yeah, it might change how we think about it, but we do still get the answer for it. Okay. Only two more. Each delta x sub I, which is just each little subinterval, may be different. Now, the good news with that is we have not seen it be different yet, so we don't really have to stress too much about it other than the fact that it could be. And then finally, the last little assumption that we make is that u sub I, which is exactly what we plug into the Riemann sum up here, u sub I right here, we'll just require is a point, and we'll just say is in the ith subinterval. Okay, so a little bit of formalization happening now. Not as formal, I don't think, as your book does it, but these are all things that we get to assume. And I'm not going to give you a function that does not exist and ask you to do something with it. That would be absurd. Okay, ears open, wide open. On the AP test, you will be doing left Riemann sums or lower Riemann sums. You will be doing right or upper Riemann sums. And the third one is the midpoint, but we'll work those points out as well. We haven't done one of those yet. Okay, with this, here's how we're going to knock this out. You will have to erase some of the work that's on the boards around the places. There will be, I'm trying to decide. We're going to do 2 groups of 2 and a group of 3. We'll work it out. There are some ground rules that we're going to use with here. Now, for those of you that are traveling on the road, I'll put the problems up on the board. What you're going to miss is I'm going to put these problems up on the board. Each of you 3 groups is going to go to a different location in the classroom, and you're going to try to work through these with your neighbors up on the whiteboard. Okay. With that said, as you're going through this, whoever's holding the marker, whoever's actually doing the writing for a problem, you're not allowed to speak. We are going to be practicing our mathematical communication in this. So one of you will be listening. The other person has to be able to speak clearly to write down what they're saying. If you and your partner are struggling with a problem, your natural instinct is going to be to ask me for help. Love it, but I'm not going to answer questions with anything but another question. I will not tell you specific answers. If my question is, am I right? I don't know. Are you? Is how I'm going to answer that question. Okay, the last one. If you're working and you don't feel that my answer, quote unquote, was good enough to help you out, the cool thing is that you have a collective, like, bunch of you in here working the same problems. You can step back, you can examine somebody else's work, you can ask that person questions, but you can't just copy. Cool. So for this, those are the ground rules. I'm going to get the following problem up on the board, and we're just going to try one of these right now. We might go back and forth, but let's get the problem. If you want it in your notes, you can. I'm going to do the problem up here after you guys do it. I'll probably just close my screen and work on it while you guys are working on it. But I want you guys to do the following. You can write it down in your notes or don't. That part is up to you if you want an extra example in your notes. Like, this is the hardest part of this for me because I really like the way that I do notes. If you want this example in your notes, I would encourage take your notebook with you and work it along while you're helping your neighbor go through it. I'm cool with that. But here's our problem. We're just going to jump right in. The problem, and I just didn't print these out, is the only reason we're writing it here. So we're just going to say f of x for this problem is 2x minus x squared. Okay, and we're just going to say for x in the interval from, we'll say it's a closed interval from 0 to 2. Okay, what I want you guys to do, and we're going to try this without the infinitely many part, you're going to partition, which Gosh, that's a goofy word. Somebody remind me what partition means? Split into parts. Good. I want you to partition this thing into, we'll do it nice, 4 subintervals. Using, and here we go. Here's A, B, and C. We're going to work them sequentially. What I want your groups to do, we'll do one group can use this board. I would just start all the way over and start working it. Don't erase stuff in between parts. Do A and B and C on the same board. If we need more space, I'll go get paper and stuff. But for A, I want you guys to do this using our left Riemann sum. Now, there's some language stuff that we have to be able to parse out: upper, lower, left, and right. Did I say upper or lower? Or did I use left and right language? I use left and right. I would keep that in mind. On B, you're going to do the same problem using right Riemann sums. And then on C, this is a fun one because we've not done one of these problems. You're going to do the same thing, but as I mentioned, it's going to be on the it's going to be on the AP test. You're going to do it with midpoint Riemann sums. Okay, for this, I have some handy bookmarks I'm going to cut out for you guys that I made to kind of help you out with stuff. They won't apply to this problem, but I assure you they will apply to stuff in the coming days. Here's how I want to do this. We're going to do 3 groups, right? Okay. 1. Cool. 1s, far board over there. 2s, do you mind if I have them work behind you? Behind Miss Sweet. 3s, right her. And we'll see if groups of 2 are too small, we may tweak these, but I want to see how it works with small groups like this. Cool. I will keep the problem up on the board for you guys. And for those of you traveling, you're going to miss a bit of stuff. I'm going to think that out for a minute, but I'll pause the video. If you guys on the road want to try to work these, I'm cool with it. Let's see what we come up with. We have Abigail walking us through part A of this problem. So go ahead, Abigail.
Okay. Wait, do I use the pen or no?
You can just scroll up and down if you want, and I can leave the pen for you if you would like it. Just in case you want it.
Okay, so what we did is we split the intervals into 4 parts. So we got 0, 1/2, then 1, and then 3/2. And then we used those numbers and plugged it into the function. And for 0, we got 0, and then f of 1/2 is 3/4. F of 1 is 1, and then f of 3/2 is 3/4. And then we added those, and we got 5/2, and then we multiplied it by delta x, which got us to 5/4. Yes.
How did you get 0, 1/2, 1, and 3/2?
Well, we started at the left, so it would be 0, and then the other left would be 1/2.
Okay, so the delta x, that you just don't see it because it's up a little bit, but you're just using delta x and doing a plus delta x also?
Yeah.
Okay. What would change if we're doing the right endpoints instead?
You would start 1/2.
It'd be 1/2 and 1 and 1.5 and 2, right? Okay. Last little piece. Like, you guys all started doing it with infinitely many, which is fine. That's what we've been doing. It makes sense for you to go that way. This group back here, they erased it at this point, and that's okay. They had it all worked out to say if I wanted to do this with 5 rectangles or 20 or 30. That's how everybody started. I tried to kind of steer you guys away from using all the sum rules and stuff. The last little thing, your job tonight. Thank you very much, by the way, Abigail. Could we give a round of applause for Abigail? All right, last little piece. You guys, you may have to reference a video. If you haven't done the right one yet, it is almost identical. The only thing that I need you to do tonight is this one. And we're just going to pretend right now, I'm not going to give you any answers, but let's see if we can't make sense of this. We're going from 0 to 2, right? And we're cutting it into 4 intervals. So these 3. This is 1/2. Do we all agree with that? Do we know how to find a midpoint? Like, could you tell me the midpoint of this first interval? 1/4? And how about this one? Huh. You have a way to find midpoints and just use different rectangles? Do it. Peace out. Your homework, I will be checking it, or Miss Sweet will be checking to see it completed. I need the midpoint Riemann sums for 4 rectangles. Tomorrow, we'll jump back into Infinity Land.